All right, guys. Now we're going to take a look at another rational function, so another one of our extended rational functions in section 8.3. And this one's going to be ever so slightly different than what we saw in example number 1. So this function that we're looking at is y equals 3 over x squared minus 16. So first we want to find our vertical asymptotes, which means that we want to take our denominator and figure out what would cause it to be equal to 0. So I can take x squared minus 16, set that equal to 0. And in order to solve this equation, I can add over the 16. And then to undo the square, I can take the square root of both sides, which means I'm going to have two different vertical asymptotes, one at positive 4 and one at negative 4. So you can have more than one vertical asymptote. There are actually situations where you could have 3 or 4 or 10 if you had a really crazy looking equation. But we'll take just a look at 2. So I've got negative 4, that's one of my vertical asymptotes right here. And then positive 4, my other vertical asymptote is going to be right over here. So I've got those sketched out, which means I'm going to want to test some points on the left of negative 4, in between negative 4 and positive 4, and then to the right of positive 4. Now my horizontal asymptote, this one, what I want to do is consider my exponents. So my exponents are the same up in the numerator as they are in the denominator as far as the highest exponent value. So I've got a squared up here and a squared down below here. So when your exponent values, the highest degree, is the same in the numerator as it is in the denominator, what you want to do is divide your leading coefficients. So in this case, what I'm going to do is divide the 3 in front of the 3x squared and the 1 in front of the regular x squared. And so y equals 3 is going to be my horizontal asymptote. So I'm going to go ahead and draw a horizontal line at positive 3 to show that I'm going to stop there. So now I'm going to need some points to plot, and I may want a few more than I actually have space for in this table. So I'll just kind of use more space as needed. So let's go ahead and plug in. We need to the left of negative 4 here. So let's do negative 7 and negative 5. And then we're going to need some in between. So this is my first vertical asymptote at negative 4. So I'm going to need some in between negative 4 and positive 4. So let's do negative 3, 0, and 3. And then I'll hit the second vertical asymptote at 4. And then let's test 5 and 7 on the other side. So we have a fair amount of plugging in to do. You may want to use your calculators to help you out with these ones. But I'll kind of do my work over here on the side so you can see what I'm plugging in as I go along. So first, if I plug in negative 7, I'm going to have 3 times negative 7 squared up top, and then I'll have negative 7 squared minus 16 down below. So this is going to end up being 3 times 49 over, this is going to be 49 minus 16. So I'm going to go ahead and grab my calculator and plug these ones in, and we'll see what we're going to get out from plugging in our negative 7. Square minus 16. Okay, so when I plug in negative 7 and I divide here, my result ends up being about 4.46 if I round. So I've got that point there. So if I plot, negative 7 is right about here, and then 4.46 is going to be right there. Then if I plug in negative 5, I'll have 3 times negative 5 squared over negative 5 squared minus 16. So this is going to be 3 times 25 over 25 minus 16. So if you plug that into your calculator, the value that I get out is about 8.3 repeating, so 8.33. So if I go over negative 5, and then I'm up here at about 8.33. So I'm bounded by the vertical asymptote and the horizontal asymptote here. So I'm going to have this shape that's sketched in between the two asymptotes. So that takes care of the left-hand side. Then I need to do the part in between my two vertical asymptotes. So let's plug in -3. So we'll have 3 times -3 squared over -3 squared minus 16, which is going to give me 3 times 9 over 9 minus 16. So this is going to be a negative result when I plug in -3. So the result that I get out is -3.86. So I'm going to find -3, -3.86 is right about here. Then I need to plug in 0. So I have 3 times 0 squared over 0 squared minus 16. That's going to give me 0 over 16, which is just 0. Now, another way I could have found that point was just by taking the numerator, the 3x squared, and setting it equal to 0. So then I can solve through that equation and find that my x-intercept is 0, which is always a useful point to have. Now I'm just going to do a little bit of erasing, so that way I have some room to plug in my remaining 3 points, my 3, my 5, and my 7. Now, while you're plugging these values in, I would recommend also generating this graph in your graphing calculator so you know what to predict as far as the shape goes. So I'm going to end up with the same result when I plug in +3 as what I get when I plug in -3. So this value is also going to be a -3.86. So I've got some symmetry about my axis here. So 3 and then -3.86 is right about there. So I can sketch these points together for what my graph is going to look like here. And then I have 2 more points to plug in. I need to plug in 5 and 7. So 3 times 5 squared over 5 squared minus 16. And you can pick any points that you like the most about your vertical asymptotes. And so when I plug this into my calculator, x equals 5, I again get out 8.33. So I've got some symmetry over on the right-hand side as well. So 5 and 8.33 puts me right about there. And then when I plug in 7, 3 times 7 squared over 7 squared minus 16. This will be 3 times 49 over 49 minus 16. And that value is going to give me 4.46 again. So 7 and then 4.46 is right about here. So this piece of the graph is going to come this way. So this is a little bit more complex rational function than what we saw yesterday, but our approach is the same. We check to see what vertical asymptotes we have, and we check to see what horizontal asymptotes we have, and then we're just plotting values around those boundaries. You always want to check these and confirm the pattern and the trend with your graphing calculator. That way you already kind of know what shape you're going to be sketching as you go along. So vertical asymptote process is always the same. Set the denominator equal to 0. But when your exponents are the same in the numerator and the denominator, to find the horizontal asymptote, just divide your leading coefficients. So for 2 regular x's, you'll just divide the leading coefficients of linear terms. For quadratics, you'll divide the 2 terms in front of the quadratic. For cubic, 2 in front of the cubic, and so on. Our last example, you guys, is going to be example number 3. And this one is just going to have one thing that's different from example 2 or example 1. So this one says y is equal to x squared minus 5x plus 4. So I want to check and see my vertical asymptote using the same process that we've used up until this point. So that means I'm going to want to take that x minus 3 and set it equal to 0, because that is going to tell me where I can't cross vertically. So x minus 3 is equal to 0, which means I have a vertical asymptote at x equals 3. So I'm going to go ahead and sketch out that boundary line vertically right here. So I'm not going to be able to cross this point here. Now, as far as my horizontal asymptotes go, this one is a little bit different. if I have exponents that are higher in the numerator, so up above, than they are in the denominator, I'm actually not going to have any horizontal asymptotes. So no horizontal asymptotes here, none here. So instead, I'm going to need to generate some additional points about x equals 3 to figure out what the shape of this graph is going to look like. Now, one thing that I usually find useful is to start by plotting your intercepts, and then you can sort of go around your intercepts. So my intercepts are going to be where this crosses the x-axis, and I can actually take my numerator and set that equal to 0 to figure out where that occurs. So if I have x minus 4 here, x minus 1 here, my intercepts are going to happen at 1 and 4. So that means I'm going to cross the axis here, and I'm going to cross the axis here. So I would recommend plotting a point to the left and right of each intercept in order to generate this graph. So what that means is I want to plot something smaller than 1. So let's do 0. And then bigger than 1, but not yet at my vertical asymptote. So I would say 2. And then bigger than my vertical asymptote, but not yet at my intercept. So I would pick 3.5 is the only really good option there. And then after 4, I could pick something like 5 to figure out what I'm going to get out. So just like before, now we've got some point plugging in to do. And I like to do this in the factored form. So I just factored my numerator over here to make it x minus 4 times x minus 1 all over x minus 3. I just think that's easier to plug into. If you don't like that as much, though, you can certainly plug into the quadratic. So I'm going to plug my points in this darker blue. So first I'm going to plug in 0. So I'll have 0 minus 4 times 0 minus 1 over 0 minus 3. That's going to be negative 4 times negative 1 over negative 3, or 4 over negative 3, which is about negative 1.33. So 0, negative 1.33 will be right about there. Then I want to plug in 2. So I'll have 2 minus 4 times 2 minus 1 over 2 minus 3. So 2 minus 4 will become negative 2 times 1 over 2 minus 3 is going to be negative 1. So this is going to be negative 2 divided by negative 1. So this is going to be a positive 2. So when x is equal to 2, my y output is going to be 2 as well. So this graph, if I connect my points, is never going to cross my vertical asymptote. But my graph is going to look something like this, just the general trend, not perfect points to the left of what I plotted. Then, if I want to plot my 3.5, let me erase this so I've got some more room to plug in. I'm still going to work with the factored form to see what I get out from plugging back into that green up there. So I'll have y equals 3.5 minus 4 times 3.5 minus 1 all over 3.5 minus 3. So this is going to give me negative 0.5 times 2.5 all over, this is going to give me 0.5. So my final output here when I plug in 3.5 is going to be negative 2.5. So if I go to plot this, 3.5 is right about here, and then negative 2.5 is right here. Then the last point that I have to plug in is 5. So if I plug in 5 back to my factored form, I've got 5 minus 4 times 5 minus 1 over 5 minus 3. So this is going to give me 1 times 4 over 2, which is just going to give me a y output of 2. So I can go ahead and find 5 and 2, and then I can sketch the shape that these points make. Again, I want to confirm that shape in my graphing calculator as well. So when my exponents are larger in the numerator than the denominator, I solve for my vertical asymptote the same way by setting the denominator to 0, but then I won't have any additional horizontal asymptotes to worry about. Your homework tonight is not too extensive. You have 3 graphs where you are just looking for where the asymptote happens. You're not actually graphing. And then you have 1, 2, 3, 4, 5 actual graphs that you just want to use 1, 2, and 3 from our examples to help you get started with. Thank you guys.